So hello, everyone. Can you hear me? Yes, I think I will stay here so we don't have problems with walking around. So I'm a chemical engineer, and chemical engineers do many things, do many great things, but one thing that we do and which we have the unique expertise in our profession is that we are the ones that design the chemical plants. So today I'm going to talk about how chemical engineers can help meet net zero decarbonization goals but faster by using math and computers to design chemical plants. So how many of you have heard before the term process design? Okay, a couple. But like most of you have not. So what I will first do is to describe how chemists design plants. So let's start with traditional process design. And in traditional process design, basically, we're given an inlet, which we call the feedstock, and we are giving a product that we want to produce, and that is the outlet. For example, let's say that, in the peak of the area where we wanted to produce ethanol, the feedstock were, for example, plants, lignocellulosic biomass, trees, and the first desired product was glucose. So process design, what we do is we try to connect the feedstocks with the products with different unit operations. A unit operation can be a reactor, can be a separator, for example, a distillation column, a flash, and a filter, and we also need to add pumps, and we need to add the compressors. So at this stage, this is called the synthesis step, and it's in where we select the unit operations and how they are connected. Then once we have this step done, and we have what we call the flow sheet, which is what we have in here, we go to a step in which we use math to model and computers to simulate what will happen if we were going to build this plant. And in the end, those simulations allow us to find out which type of equipment we have and which are the sizes that we have for each equipment. With that sizes, we perform the techno-economic analysis and the environmental analysis. And that is, we know how to calculate the operational cost of the plant, the capital cost of the plant, and also how much CO2 are we emitting, how much water are we consuming. And the important thing from this step is that these are not things that are set in stone. There are many things that you can change in the design of a chemical process to, for example, reduce the emissions or, of course, reduce the cost. So this is not an easy problem, and this is something that takes a lot of time. But things get really, really complicated when we have to design among many different technological options and, for example, many different intermediates, as is in the case that I'm showing here in the figure. So my group specializes in solving this type of problems, and we use what is called superstructure-based conceptual design to rapidly screen among many options. So it's not that we design one by one of the processes that will take years of time, but we use some other tools to, for example, answer questions like, is the optimal pathway always the same? And there are very different assumptions, so there is something that is really, very competitive out there. Which are the bottlenecks? Which are the steps that are causing like really high emissions or are causing a lot of cost in the plant? And how, of course, can we make this process, how can we improve this process, and how can we make it cheaper or cleaner? So I'm going to talk today about two examples that my group has studied in the past years. The first one is green hydrogen. So we heard a lot about green hydrogen here yesterday, and green hydrogen has a lot of current uses. It's one of the main feedstocks in the chemical industry. And basically, we use it in oil refineries, we use it for production of fertilizers and ammonia, and we use it in metallurgy, among others. But the real game changer for hydrogen are the projected uses. One of them, for example, is that hydrogen can be used in electric vehicles for heavy-duty transportation, and the idea here is that we feed hydrogen in the anode, we obtain the electrons move the electric motor, and then in the cathode we combine with air and we get water as emission. So there is no CO2 associated in here. And another projected use is to use hydrogen and combine it with carbon capture to produce what we call drop-in hydrocarbons. So these are the same hydrocarbons that you obtain currently from oil, but they are obtained for captured CO2. And this pathway is very important, for example, for sustainable aviation fuels, for which we don't have any other non-carbon-based technology right now. So this pathway can be potentially net zero if we design it properly. So I hope I have convinced you that hydrogen is great and is great for the future. But the problem with hydrogen is that the way we produce it right now, which is by a technology called steam methane reforming, actually produces CO2 at the production stage. So this is not, in the life cycle, this is not sustainable. So there are other ways to produce hydrogen, and the way that we are really excited is the one that we call green hydrogen. And green hydrogen has 0 CO2 emissions associated. How is green hydrogen produced? Green hydrogen is produced by electrolysis of water, and we power this electrolyzer only by using energy that comes from renewable resources, preferably wind, solar energy, or hydropower energy. So my group has studied this for a very long time, as I said before, and we were interested to find out how to produce hydrogen at a minimum cost. So using the process design framework that I talked at the beginning, what we find here is that we identify the feedstocks are going to be the renewable electricity and the water, and the product is going to be, for example, a demand for hydrogen to fuel a fleet of trucks or buses in a certain city. So let's build the flow sheet together. There are 3 possible electrolyzers technologies. We have alkaline electrolyzers, which is an old technology that is it's cheap right now, but it's not very flexible. And it will become clearer later why we need the flexibility. Then we have the star right now of electrolyzers with the polymer electron proton exchange membrane electrolyzers, which are very flexible but are not cheap. And then we have a newer technology in the market, which is the solid oxide electrolyzer, which is somehow flexible, very efficient, and potentially cheaper than PEMES. So that's on the technology side. But then, how are we going to connect these electrolyzers? There are maybe like 3 possible supplies of electricity we can connect to the grid in situations where the grid is completely green. We can use only the surpluses of this grid, and this is because probably in settings where you have renewable electricity as the major contributor, the prices are going to be varying day by day, so it may be cheaper to just use the surpluses, or you may install your own solar or wind generators, and then you have, you have to live with all the up and downs of these types of generation. So the common feature of these sources is that they will all be intermittent. Intermittent in terms of prices, if we connect to the grid, intermittent in terms of the availability if we connect only when there are surpluses or if we connect directly to the generators. And for process design, this is very important because, as I mentioned earlier, we need to design which is going to be the size of our equipment. But right now, we have 2 limiting types of sizes. So one is, so we oversize our equipment and we are able to capture, all the resource when it's there, but most of the time the equipment is not going to be used, or we design on the other limit where we design an equipment that is always on, but actually cannot capture all the ups and downs of the electricity. So that introduces a lot of problem when we are trying to solve a design for this system. In addition, some other decisions that you need to make is how I'm going to store the energy. And you have here, why do you need to store here things? That is because you have a variable supply and a variable demand. So to match the supply and demand, you will need to have storage at some point. The storage can be as batteries before you convert the energy into hydrogen, or it can be as tanks after you convert it into hydrogen. So this problem that seems to be very innocent because it doesn't have many options, actually, due to the intermittent nature of the resource, it is a system of equations that has more than 200,000 equations that need to be solved simultaneously all at the same time. So it is a very large and very difficult problem to solve. Evidently, you are not going to solve this by hand. We use computers, and that is what my group does. So what we fortunately were able to solve this problem, and I'm showing here some results. These results were, so the numbers were obtained from a case study that we did for Uruguay, which is a small country in South America that has completely decarbonized the electricity mix. So they were interested in studying how to decarbonize the transportation, public transportation. And on one end, they were thinking about putting small isolated fuel stations that had, that either connected to the grid or had their own wind and solar generators. And on the other side was, okay, so maybe we just, need to have a centralized large facility for hydrogen production. And so which will be the optimal process design for both cases. What we found here is that when you are looking for a small hydrogen demand, the most optimal solution is to only work with one electrolyzer and to connect to the grid. Whereas if you have like a very large, if you are looking for a very large demand, then you need to combine several types of electrolysis technologies. You need to have your own solar and wind generators, as well as being able to connect to the grid to stabilize your operations. And then in this case, you also need to have batteries to stabilize the operation of the electrolyzers. In terms of costs, we found that for the large scale production, we were hitting the goals that these facilities had in the country, which were around $4 per kilogram of hydrogen at the time. Now we are thinking that we will need to go for $1 per kilogram of hydrogen in the future. So there is still a lot of things that we need to do to improve these processes. Let me go quickly to describe another case study in which we are trying to apply these ideas, and this is to decarbonize the chemical industry. So you know that chemical industry has very ambitious decarbonization goals. The problem is that they already have a lot of equipment that, discarding the equipment is not going to be efficient and is not also going to be sustainable. So the problem they are facing right now is which is the technology that I need to adopt to comply with my decarbonization goals, but also not destroy all the equipment that I currently have. So which are the options that we are considering? This is a case study that we are doing with oil refineries. So oil refineries mainly need process heat and hydrogen. Hydrogen we have discussed before how to decarbonize it. We can also do, as we are doing right now, with steam methane reforming and added carbon capture units. For process heat, we can use e-boilers on, if we are going for very high temperatures, the only option right now is to use carbon capture units. So to give you a flavor of the results that we can get and how are we going to be using this type of optimization frameworks, what we are doing right now with how things are done for the industry that is supporting this project is that in the optimal solution, we are decarbonizing just using carbon capture units for the first 10 years, and then only moving to electrification when we have very stringent decarbonization goals. But now that we have built these problems, we instead of just, answering the question which is the best solution for the problem that you have right now, we can also use these tools to answer different what-if case studies. And one of the things is, for example, what will happen if we introduce carbon taxes? Are we adopting earlier electrified technologies, or are we adopting earlier carbon capture technologies? What will happen if we, for example, lower the price of electricity? What will happen if we can play with having, intermittency around? So these are the type of questions that my group is interested in answering, and I'm happy to answer any question that you may have. Thanks a lot.